recording.
Sure. Yeah.
So I'd like to start this call in the CSIG weekly series. Agata Mosinska from Lausanne is going to speak today. So I'm handing over to you, Agata, and we're recording now.
Thank you. So good afternoon, everyone, or good morning, depending on where you're now. My name is Agata Mosinska, and I am a PhD student at Computer Vision Lab at EPFL in Switzerland. And today I'll talk about the topic of my PhD thesis, which is detection of curvilinear structures in images. So linear structures are prevalent in nature. And they appear on a range of scales, starting from neuronal membranes in electron microscopy images to the whole neurons in light microscopy, blood vessels in retina and eye, cracks in different materials, and finally to roads in aerial or satellite images. In our lab, we work with all those kinds of data. And we aim at creating algorithms that are general enough so that they can deal with all those different kinds of networks. But why do we actually want to detect linear structures? I will give you a few motivations. Detecting neurons can help us, for example, to resolve the brain connectivity, which is extremely important to simulate complex processes that are happening in our brain. Detecting blood vessels, in this case in retina, it's very useful for diagnostics, for example, of diabetes. And finally, detecting cracks in materials is useful for studying material properties or stress analysis. And last but not least, detecting road networks is important for autonomous driving and also for quick updates of new maps. However, this is not an easy problem, and there are a few challenges associated with it. So first of all, usually detection of linear structures requires some large context, because just to give an example, we have here two crops of two different images, really zoomed in. And if you look on the left, for example, it's difficult to tell whether it's a part of the road or maybe it's a roof. On the right, it's an image of a concrete, and it's difficult to tell whether there is any crack in it, and if so, where exactly it is. However, if we look at a bigger context, it's easier to tell that the thing on the left, it's actually a roof, so it's not a road. We are not interested in segmenting it. And on the right, there is indeed a crack in the concrete, and it goes through the middle of the image. We also have quite a lot of occlusions, especially in satellite images, where we have for example, trees occluding roads. So humans are very good at telling that, for example, if there is a road coming into the forest and then there is a road coming out of the forest, then it's very probable that there is also a road occluded by the trees. However, for the algorithm, it's still quite difficult to do it. Also in biomedical or medical images, there might be quite a lot of noise due to some equipment issues or maybe uneven preparation of the samples. And we have to also deal with this kind of problems. And lastly, there is a really large variability of appearances of linear structures. So in case of aerial images, we want to detect both big motorways as well as some small dirt roads. In case of medical images, we may have scans corresponding to healthy subjects, and also those corresponding to diseased ones. So they also look quite different. So our algorithm should be flexible enough to deal with all those kinds of appearances, but also it should be able to filter out line-like structures that we are not interested in. So for example, on the left, you can see that we have some river, and it actually may look like a road, but yeah, we are not interested in detecting rivers. So our algorithm should be able to discard those detections. So now that I talked a bit about the motivation and challenges that we face, let me go on to the technical part. So how do we actually detect linear structures? This is usually a two-step process. So once we have an image, we first perform segmentation. So we assign a probability to every pixel, depending whether it's our structure of interest or if it's a background. And once we have a segmentation, we can recover the connectivity of our network, the graph. And I'll talk about it a bit later and why we want to do it. But now let me go on to segmentation. So in this case, just like in many other computer vision applications, state-of-the-art approaches for segmentations are based on convolutional neural networks. And here we have an example of such network. It's called UNet because of its U shape, and it's composed of two parts. One is downsampling part, encoder, which extract features, and the other part is decoder. So it upsamples our features, and it gives us the final prediction. So this kind of network gives us a structure prediction. So we can feed pretty large patch into the network or even the whole image, and at once it gives us the whole prediction. However, during training, this kind of networks are still trained using binary cross-entropy. So in order to assess how good is prediction compared to ground truth, we compare them pixel-wise. And this is not how we as humans really do it when we look at the such structures. Because, for example, let's say that we have a small mistake. In the prediction, we have a small gap, which basically introduces a hole in the prediction. So in terms of the pixel accuracy, it's not a big mistake. It might be just a few pixels. But in terms of the topology of the prediction, it already influences it quite a lot. And this kind of properties are not captured by binary cross-entropy. So we propose a bit different approach. We proposed a new training loss term, which we call topology loss. And the idea is pretty simple. During training time, apart from comparing prediction and ground truth pixel-wise, we also compare some higher level features corresponding to prediction and ground truth. In order to do that, we use a pre-trained network, in this case VGG, to extract features from both prediction and ground truth, and then we compare those two sets of features using just mean square error. And in the end, we train our network using a combination of binary cross-entropy, the pixel-wise loss, and our topology loss, which compares the higher level features of prediction and ground truth. In order to understand a bit more what's the difference between the binary cross-entropy and our topology loss, let's look at the toy example. So this is a synthetic example. On the left, we have a ground truth, which is just a simple line. And then we have 4 different predictions. In all those cases, binary cross-entropy loss is the same because we misclassified the same number of pixels. However, as you can see, the topology loss, so the number under the prediction, differs in those cases. In cases where we alter the structure of the prediction more, so for example, if we introduce a lot of cuts, or if we introduce a lot of small components in the background, then it's higher compared to the situation when, for example, we have one big gap, or if we have one additional component in the background. And this is because in the cases where we have a lot of cuts or a lot of noise in the background, the structure of the prediction differ more. So the binary cross-entropy cannot differentiate between those cases, but topology loss is indeed higher for the cases where we have more topology changes. The idea of using a pre-trained VGG network to extract the features was coming from the fact that we thought that if it is trained on a really big ImageNet data set, then at least the lower layer should be able to extract some features such as smoothness of the line or continuity of the line. And in order to check that, we indeed looked at the activations of some of the layers corresponding to ground truth and prediction. So on the top you can see ground truth and an example of prediction, and then the next two rows are examples of two activation maps. So as you can see, the first example of the activation, in this case, the channel that produces this feature is responsible for elongated vertical structures. So this kind of features, they will ensure that our prediction is smooth. On the other hand, the bottom row shows an activation of the channel which is responsible for small components in the background. So this kind of features, they will ensure that we suppress the noise. So if you're familiar with the style transfer, you can probably see some parallels to the perceptual loss, which is also defined using VGG features. And in that case, the perceptual loss measures the difference between the content of the original image and the generated image using those higher level VGG features. In that case, the features extracted from VGG are used for computing the loss because we do not have the direct ground truth for the generated image. So there is no one definite ground truth in this case. In our case, however, in case of segmentation, we do have access to the precise ground truth, but still it turns out that it's more beneficial to train the network using pixelwise loss and the loss taking into account higher level features than just by comparing the prediction and ground truth pixel by pixel. And also in case of style transfer, VGG network is applied to natural images, and it's also pre-trained on natural images. And in our case, we use a network pre-trained on natural images to extract features from binary masks. So this was also for us an interesting insight that it still works, even though the images come from two different domains. So just by looking at qualitative results, we can see that the predictions that we obtain by training the network with binary cross-entropy they have more noise in the background, and also the lines are not as structured, they are not as smooth as compared to the predictions that we obtain when training the network using topology loss. Here we have some more examples of the results that we obtain with neuronal membranes in electron microscopy images. Another improvement that we added to our segmentation process was recursive refinement. So this is not a new idea. Usually it is done by stacking a few networks on top of each other, where every next network kind of improves the prediction of the previous network, and we feed an image and the previous prediction to the next module. The problem with this approach is that in this case the number of parameters grows really fast, and this might be a problem when we have a small data set, like which is often the case in medical domain. So what we propose instead is to use the same network to kind of refine its prediction. So we enter into the network a few times, an image and previous prediction, and the network kind of learns to correct its own mistakes. So it accumulates the error, and at the end, hopefully it can correct its own mistakes and improve the final prediction. And as you can see, this approach is quite useful for example, closing some small gaps in the predictions, and also making the prediction more certain in some regions.
There's a question for you in the chat. Do you get
Yes.
better results when you intelligently pool all the models over any one approach? I know that is a Kaggle master trick, and they get very good at combining models for better results than previous single best.
So you mean just using a few different models to
yes,
like
if you combine them.
Yeah, so this is so we haven't tried combining a few different models. This is one of the strategies that, of course, we could do. The advantage of this recursive refinement compared to training a few different models is that this refinement strategy is kind of trained end to end. And while for different models we would have to train them separately, but yes, we could think that it's kind of similar approach. And also in the case of recursive refinement, as I said, that the network is supposed to learn from its mistakes, while in case of many different models, that the models are kind of independent. So we may see it as a good or bad thing. Okay, so just by so far I was talking about the first step of our detection pipeline, which is segmentation, and now let me just talk about inferring the final connectivity of the network. So this is very important in some applications, such as, for example, neuroscience. And here we have an example of a 3D scan of neurons in the rat brain. And what neuroscientists are really interested in is how many neurons are there present, what is their connectivity, what is the branching pattern. And for that, we really need to have a graph representation of this network. So we could say, okay, we have already a segmentation, so maybe we can just threshold it at some probability value, and we look at the connected components, and maybe this is enough to get the graph representation. However, this is not the optimal approach, and this is because the segmentation still sometimes it's not perfect. It contains some mistakes. Like for example, on the left, you can see that there are some gaps in the prediction. Maybe there's no road indeed, or maybe there was it's just occluded by trees. On the right, on the other hand, it's a skeleton of neurons that we detected. And what happens very often in that case is that there are two neurons very close to each other in a space, and sometimes the two separate branches in the prediction, they get merged into one. So we want to figure out whether the two branches are really connected, or maybe they should be separated. In order to do that, we have to look at long-range relationships between different segments of the network. And in order to do this, we do what we call path classification. So this is a simple idea where once we have a segmentation, we sample many different paths from it. So these might be paths, for example, between two junctions, or between two endpoints of the prediction. And for example, the paths between two endpoints, they have a potential to bridge the potential gaps in the result. Of course, not all of those paths that we sample, they will be positive. So the really true paths, some of them, they will be crossing backgrounds, and we want to filter them out. So on the left, you can see a few examples of the negative paths, and on the right, a few examples of positive paths. In order to classify them as positive or negative, we extract some set of features that describe the curvature of the path and its neighborhood, and then we train a classifier to actually assign a probability whether it's a positive path or negative one. So far we use some handcrafted features, and we train a separate classifier, but we are looking into ways of using some deep features and maybe training the segmentation and path classification together at the same time. And here we have an example of how this path classification may help. So we have an image. On the left, in the middle, we have a segmentation that is not perfect. So as you can see, some things are missing, some connections. But then if we sample a lot of paths, as you can see on the right, and we assign probabilities to those paths, some of those mistakes, they can be corrected. So, for example, as you can see, the path that is pointed by the green arrows, even though it's not present in the segmentation, once we draw a path between the two endpoints and we classify it, it actually turns out that it's a positive path. So here on the right, the paths are color coded, and red means that this is a very probable path, and blue means that it's probably a negative path. And finally, if we want to ensure that our network is, let's say, connected with some kind of selected route, or that we have a tree structure, so without loops, or maybe you want to allow loops, we can write an integer program where every path is treated as a binary variable, and then at the end of the optimization, when we try to minimize the cost of the subgraph, if the variable gets assigned 1, if the path gets assigned 1, then it means that it should be left in the solution, and when it gets assigned 0, then it means that we should discard it. So just to sum up, we can look at this detection pipeline at various different scales. So first we perform segmentation, which is just basically pixel classification. Once we have a segmentation, we can classify paths, but by looking at longer range relationships. This way we can build a graph of some larger neighborhood consisting of many different paths. And finally, if we repeat this procedure for different regions, we can obtain a large-scale reconstruction. For example, in this case, we have road networks in some city, or it can be also neurons in some part of the rat brain. And just to conclude what we've said today, in order to perform delineation well, we have to look at the larger context in the image and also take into account some higher level features of the linear structures. And those higher level features, it turns out, it can be quite well approximated by features extracted using some pre-trained models like VGG. And by reasoning about the long-range interactions between the linear segments or paths, we can in the end recover the full connectivity of the network of interest. So this is it from me today. Thank you very much for your attention, and I'll be happy to answer your questions if you have any.
There is another question for you, Agata. Thank you for the fabulous talk. The question says, can you see your possible improvements in neurological and vision helping teach future MDs?
So I think it's definitely, so I think it could be very useful, and actually we are working with neuroscientists, so not with doctors, but more like neuroscientists, and they really have huge amounts of data. For example, the scan of the whole rat brain, and it's just not feasible to annotate all of this by hand. So annotating one neuron, they told us it may take 3 weeks. So if we can use this approach to actually help them to reconstruct neurons in the brain, that should be much faster, and it should also allow us to discover some patterns in the brain, or maybe even some new kinds of neurons.
That's great. Thank you. I see Scott has unmuted himself and he has a long question for you. So maybe, Scott, do you want to go ahead and ask it?
Thank you, Agata, very much. Very interesting. Conceptually, in what ways would new modeling be involved at the atomic level on linear structure? For example, with expansion microscopy, since you've mentioned the neuronal and sort of the street view levels, are there, when you go between scales, say in going between street view and the neuronal level, do you add new modeling approaches, and would you add a new one when you got even smaller to the atomic level?
So we follow the same procedures, whether we work with neuronal structures or whether we work with roads. So we try to have the general approach, but we have we use different data sets to train our networks. But you're right. Sometimes it could be beneficial to use some prior knowledge that we have about the task that we're dealing with. So, for example, in terms of neurons, we know that that they always form trees, so they are no loopy neurons. And if we add this kind of prior knowledge to our algorithms, then we can potentially obtain better results. We had also at some point one idea that we could use some transfer learning, so that, for example, we have we have a lot of examples of maps that are just freely available, and some annotations from OpenStreetMap. So, for example, we could train our model on roads, and then maybe use it in the task of detecting neurons. But this is still, I think, in the future work. But yeah, that would be really interesting.
Thank you.
Thank you. And there's another question for you from Corbin. I don't see him unmuting himself, so I'll just read it. What type of satellite imagery are you using for ground surveying? The quality of, yeah, and...
yeah, I can ask.
Oh, go ahead. Please go ahead.
Sorry, I was just having some technical difficulty. So I was wondering what type of satellite imagery you use for your ground surveying. So the quality of the image and the information that you're able to glean from the image is determined by the satellite. So for example, ASTER versus LiDAR versus hyperspectral imagery is going to allow you to assign whatever material you're looking at based off of its spectral signature. So the satellite is going to be able to read, all right, is this concrete? Is it tin? Is it aluminum? What mineral is it? Whether it's salt or if it's, quartz grains. If you're able to unmix those spectral signatures and assign them into a category, perhaps you would be getting better results as to, the linear structures as far as differentiating a road from the rooftop of a building. And perhaps you could even apply that methodology to neural structures as well.
Yes, definitely. So in our case, we just use RGB images from Google Maps. So we don't use any spectral information, and the reason for that is that it's just very easy to get ground truth for this kind of application. It's not the perfect ground truth. It's a bit noisy, but we just get it for free basically from the maps. But as you said, if we use some spectral information, I think definitely it would help. And I know that there are now some initiatives that actually aim at creating really large data set of spectral images from satellites and with very precise ground truth. So yes, I think it's an interesting future direction for work.
Right, and I totally get that. That was a part of my undergrad, so I've done a lot of research on that, and I know that those images are expensive to actually get from professional organizations. But I know that NASA's Jet Propulsion Laboratory has some software for free if you're able to go in through your university that's going to be able to allow you to unmix some of those images. So just check that out.
Okay.
I added you on LinkedIn, by the way.
Great.
So if you just want to check out the presentation that I did on there, maybe it could be a help to you, maybe not. But thank you for the presentation. It was awesome and very interesting.
Thank you very much for your advice. Thanks.
Thank you, everybody, and thank you, Agata, very much, and good luck with your PhD as well, and all the hard work you're doing at the moment. And please thank Agata if you enjoyed this talk in the chat, and good luck.
Thank you very much for the invitation.
Thank you for taking the time to speak with us. Thank you. I'll just let people do the thank yous, and then I'll stop recording. Thank you, everybody.